Welcome everybody. Yesterday I presented this talk at a conference. Today I want to re-emphasize some main points and re-present the talk without the time constraints. The subject of the talk is n-scale calculus, which has been recently developed, and its possible uses in physics and some future opportunities about this field of research. First of all, in order to define n-scales, we need to remember what timescales are. A timescale is an arbitrary closed subset of the real numbers R in the usual topology. In the usual topology means open intervals are open sets. This is the usual topology on R. For example, the set of integers z, the closed interval 0, 1, and their union, as well as the real line itself, are all examples of timescales. Since they are one-dimensional, in the language of or the jargon of n-scales, timescales are just called as one-scales. Here we see the integers as a timescale. This is the closed interval 0, 1, and this last figure shows the real numbers. The timescale calculus was developed by Hilger in 1990s. There are a few new concepts in this calculus. For example, the forward jump operator sigma. It is used to define derivative in this context. It is defined as follows. Let t be a timescale. Then for any t in capital T, we define sigma t as follows. In a way, sigma t is the next element of the timescale that comes after t. If sigma t is t, the point is called right dense. If sigma t is greater than t, the point is called right scattered. For example, here, if t is 0.5, sigma t is again 0.5 because the region is dense. In the case of integer, for example, the 0, sigma 0 is 1 here, so sigma 0 is not equal to 0, so the point is called right scattered. Similarly, one can define backward jump operator rho. Its definition is similar to that, but instead of infimum, one uses supremum, and here one uses s less than t condition. There are more to cover about timescales. The interested audience may see Borner and Peterson 2001. This is a great book. I recommend it to everyone. The definition of Hilger derivative is what I will talk in the slide. Let t be a timescale. The Hilger derivative of a function ft on t is defined as follows. It is defined through this limit. If the point is right dense, this is the usual derivative we all learn in calculus classes. However, if the point is right dense, the Hilger or delta derivative of f equals delta f divided by delta t. It is similar to difference operator divided by the distance between the coordinates. The use of sigma in this definition gives us delta derivative. One may also define what is called as nabla derivative using the backward jump operator rho. For a right scattered point, the derivative corresponds to forward difference operator divided by the distance between the t coordinates. For a right dense point, this is the usual derivative. The integral in this context is defined in a similar manner. The Hilger derivative of the integral is equal to the function that is integrated. Now let's talk about n-scales. Similar to the definition of timescales, which are just one-scales in this context, n-scale is an arbitrary closed subset of Rn in the usual topology. This is the conference this work is published in a conference proceedings. I will let you know the references at the end of the talk. However, one also needs to impose a neighborhood relation in the form of a directed graph in the most general settings. Because without the neighborhood relation, forward and backward jump operators cannot be defined. However, if the n scale is a product of n one scales, the neighborhood relation is inferred from the product space structure. For example, let's see a simple example of a 2 scale. There are 6 points here. The directed lines shows us the neighborhood relation in this context. For example, using sigma operator in this direction, one may jump from 1 to 5, and if you use backward jump operator in this direction, one may jump backwards from the point 5 to the point 1. The derivatives on n scales is similar to the definition of derivatives in the case of time scales. However, in this case, we have an upper index I to denote which direction one uses. For example, it's like a partial derivative. If the point is dense then in the right direction, then the usual partial derivative is calculated. However, otherwise, when sigma I x is not equal to x, we have a similar definition that we have seen in the case of time scales. The derivative is defined in this way. The integrals on n scale is defined in a hand-waving way in this preceding contribution. Dündar 2018, but a more rigorous proof is needed. So if you like to develop n-scale calculus, this is a good way to start improving it by defining integrals in a solid way in this context. Local dimensionality. The dimensionality of an n-scale may differ from one point to another in a local way. It may be defined using the number of neighbors a point has. Wolfram model, Wolfram 2020, cites a method to define a local dimension. One may see this reference, which also cites another 2 references. For an n-scale that's the product of n1 scales, the local dimension is always n. However, in the figure below, which I call the set 8, or you may call the set infinity because it looks like the infinity or the 8 number, the number 8. The point at the center has local 2 dimensions. Why? Because it has 4 neighbors, and any other points have local 1 dimension. For example, this point have 1 incoming edge and 1 outgoing edge. So we see that it's locally 1 dimensional. However, the point at the center is 2 dimensional. In this slide, I will talk about possible uses of n-scales in physics. This space-time we encounter in general theory of relativity has 4 dimensions in the usual settings in our universe. However, at the Planck settings, there are indications that the number of space-time dimensions may be just 2. Kalib talks about this information in his paper. For example, therefore, as we have seen in this figure, in n scales, one may define dimensions locally, so it may be useful to use or to consider using n scales in quantum gravity research. Since n scales are a flexible construct, they may model the spacetime geometry at all scales, from Planck scales to galactic scales. For example, inside of a black hole may be modeled as a discrete lattice, whereas the outside of the black hole may be modeled as a continuous spacetime. There are 2 theories, for example, just to give an example, loop quantum gravity and causal dynamical triangulations. Approaches to quantum gravity use discrete spacetime structures. So maybe using n scales in this context may be useful. These are just speculations. One may also define quantum field theory on an n scale. For an example, see Dündar and Arık 2018. In this study, we considered an n-dimensional spacetime as a regular discrete n scale. Regular discrete n scales means that Regular means we are taking the Cartesian product of time scales. Discrete means sigma t is not equal to t at every point on the space-time. So the space-time is discrete. What we have found is that, how to say it, if there is a discrete dimension in space-time, it has either cyclic boundary conditions or it has to be bounded. Otherwise, the mode solutions diverge. This is one study. We have also defined exponential functions on regular n scales in a study that will be published in the future with my colleague Bayram Sözberk. And using the definition of n scales given there, one may also define, as a simple example, U1 gauge theory on regular n scales. You can see the definition of n scales. You can see the definition of exponential function on n scales on ResearchGate. It is an older version. We have renewed it and went over it one more time to make the proofs of theorems more solid. So hopefully it will be published in the future. These are the possible uses of n scales in physics. Let me talk about the Wolfram model, which is also a discrete model. It's been introduced in the first half of 2020. These are the references. This reference has come in recent month. It's also interesting. One may also like to see, which is put later. The universe as a whole in the Wolfram model and its contents are described by a hypergraph. What's a hypergraph? Hypergraph is just a graph where hyperedges may connect more than two vertices. This is called as a hypergraph. A one-step time evolution of the universe is the application of a rewrite rule that acts on the hypergraph. For example, this is a rule. This is a rule that converts this type of hyperedge to this type of hyperedge. This is a summary of the Wolfram physics model. You can see it on the website I have cited here. It's an interesting model. It has been shown to have interesting connections with the known physics such as quantum mechanics and general theory of relativity. This is just a summary of the Wolfram model. For more, you may see this website, www.wolframphysics.org. Conclusion, we have talked about one scales, which are time scales, and then about n scales. Derivatives are, and we have talked about derivatives and integrals on n scales. It would be useful to use n scale as the space-time structure in quantum gravity applications, such as, for example, the number of dimensions that a point has may be defined locally. It handles continuous and discrete space-time in one framework. The difference between the Wolfram model and the n scales is that n scale is not a complete theory of the universe. It's just a framework where one can use some analysis techniques such as derivatives and integrations. One may also consider hyper-n scales, which may generalize the hypergraph structure in Wolfram model, but they are not guaranteed to be useful. This is yet to be seen. The difference between the hyper-n scales and just hypergraph is that in hyper-n scales, one may also have dense regions, continuous regions. It may be interesting to consider, but I do not guarantee that it will be useful. This is just a speculation. All in all, n-scale calculus can be used where some of the domain is discrete and some is continuous. For example, the interior of the black hole may be discrete, whereas outside of the black hole may be continuous. So I think I reached the end of my talk. So thanks for listening. My name is Furkan Semih Dündar. This is my personal website, which is in English. Let me show you the references, each slide for 3 seconds, just in case you may take notes. This is the book I talk about, Dynamics Equations on Time Scales, in introduction with the application. This is the paper of the Carlip that I mentioned. This is the preceding paper in 2018, where I put forward the theory of n scales. And this is the paper where me and my PhD advisor in the past used n-scale calculus to define scalar field on regular n-scales. This is the definition of exponential function. You can find it on ResearchGate. Gorath, Jonathan, these are the two papers by Jonathan about the Wolfram model. This came later on. It's about algorithmic causal sets and the Wolfram model. This is a seminal paper of Hawking in 1975, particle creation by black holes. This is the study where Hilger first introduced the time-scale calculus. This is about causal dynamical triangulation, and this is about a review paper. These two are review papers. And this one is about the loop quantum gravity. And finally, the Stephen Wolfram's paper, which is a very long paper. It's about the Wolfram model. So, thanks for listening. If you liked the presentation, please like me on YouTube. So, thank you.